to this presenter view. Turn on this laser pointer. All right. So again, our three-legged stool that we've been looking at all quarter long, 3 steps to reduce emissions. Stop burning as much ancient dead stuff by making things as efficient as possible. The next step, and these again can all be done at the same time, is stop burning as much dead stuff in cars and buildings. So electrify everything, turn our internal combustion cars to electric vehicles, turn our natural gas water heaters to electric heat pump water heaters, etc. And then the final leg of the stool is to stop burning dead stuff to make electricity. So that's what we'll be talking about today, is greening up our electricity generation supply side. All right, so if we look at global CO2 emissions from 1990 to 2018, this big red portion, so it's at least like 30% for emissions, 25 to 30%. And this is all from coal-fired power generation. So figuring out how to get rid of this chunk and replacing it with renewables would make a huge dent in our global CO2 emissions. If we look at the global electricity mix, we are moving towards solar and PV. Solar, PV, and wind, these have the fastest growth rates, but we're still burning a tremendous amount of coal. Here in America, and then especially in China and India. And to the extent that we're not consuming as much nuclear or producing as much nuclear power or coal power, we're replacing that with gas-powered electricity, which is also greenhouse gas intensive, as we'll see. Okay, so looking at this pie chart in actual table, so we can glean some data from this. Total generation, again, is still dominated by coal for electricity generation globally. So the share of electricity generation back in 2000 was 39%, and it's only gone down a percentage. Here in America, it's gone down tremendously as we phased out coal power plants for natural gas power plants. But again, with the rapid economic development in China during the 2000s and now India during the 2010s, a lot of coal power is being built in Asia, and they're building everything. They're building wind, solar, hydro, nukes. They just need as much electricity as possible to drive their economies, and so coal is part of that portfolio. Fortunately, oil combustion for electricity has gone down significantly as a percentage share. Oil is still burned in many island communities. I've seen an old oil power plant in Kauai. I've seen them in Lamu, Kenya. I've seen them in the Maldives and in Ifati and Madagascar. So these island locations where it's the wonderful thing about oil is you could just put it in a barrel and ship it around the world. And so these power plants rely on that. Easily storable and easily transportable fuel to make electricity. But that's going down as solar and energy storage is taking over from oil production. Gas has gone up. You know this. It's because of horizontal drilling and fracking in the 2000s made gas really cheap. It's also less polluting than coal, so nation states that have abundant gas and the money to do so are switching from gas or coal to gas. Nuclear has gone down significantly. Nuclear is really good from a carbon perspective. It has nearly zero emissions, just some emissions associated with refining and purifying the uranium. But it's gone down just because it's really, really expensive way to generate electricity. It's not that expensive from an actual acquisition and production standpoint, but it's expensive from an insurance standpoint, right? Nobody wants to own a nuclear power plant because if it goes wrong, then you're responsible for a global disaster. Hydro has stayed pretty steady. Not a lot of hydro development, big hydro anymore, but a lot of micro hydro, run-of-the-river hydro still going in. And then the rest is down here. Wind and solar has grown the fastest. So if you look at their growth rates, 12% for wind year on year and 30% year on year growth for solar voltaic. So these are the fastest growing supplies of new electricity generation. But they still constitute a very small share. So they're growing super fast, but they're growing from a very small number to a very small number. But hopefully that's still changing, right? That's the nature of exponential growth. At a growth rate of 31%, that means it's doubling about every 2.5 years. You can figure out the doubling rate of something by just taking 72 and dividing it by the percentage growth rate. It's just a weird fluke of the natural logarithm. You can look at the mathematics behind that quick and dirty rule. But in general, you just take the number 72, divide it by your growth rate, and that's your doubling rate. All right. So moving on. U.S. carbon dioxide emissions by sector and fuel. So we're again talking about electricity today. So let's look at this part of the graph. And from 2000 to 2018 or 2017, we can see that the emissions are dominated by coal still. It's not the percentage of electricity isn't dominated by coal. It's just for every unit of electricity you make with coal, those emissions are really huge. So we need to get off coal. Looking at CO2 emissions for the U.S. specifically, we had a drop from 2005 to 2010 because of the recession. We'll see something similar with COVID-19. And then we've slowly been decreasing over the last 5 years or so, and or staying steady despite growing economic growth and growing electricity consumption. That's because we're switching from coal to natural gas here in America. But that's not what's happening in the world. Global CO2 emissions are still growing, not quite exponentially, but linearly at this point. And it's mainly due to growth in China from 2000 to 2010-ish, and now growth in India from 2010 to present day. And so, yeah, these economies are growing rapidly. It's a good thing. It's a great thing for quality of life and happiness index, etc. But it can be a bad thing for the environment if we just do it without, foresight of where we're getting this electricity from. And from lecture number 1, recall that we're around like 39 gigatons of CO2 per year now. So we're still growing. If you want to look into all these, where I got most of these figures, you can check out this World Resource Institute.org website for a lot of great data visualizations. All right, so this is similar to what we just saw on the other slide. It just breaks out some of those other countries. So you can see China's tremendous growth from 2000 to 2010, and now India's growth from 2010 to 2018. USA and European Union are falling despite growing economies, again switching from coal to gas. Zooming in on Bellingham, this chart's a little difficult to parse because it kind of changes each section. These colors represent years: 2000, 2005, 2012, and 2015. What we want to look at is electricity generation, mainly in commercial and residential. So you can see that electricity generation for 2015 emitted about 170K commercially and another 150K residentially. So this is a large proportion of total Bellingham emissions is electricity consumption in commercial buildings and residential buildings. And that's due to the fact that PSE has a relatively carbon-intensive grid compared to other grids on the West Coast, and especially here in Washington State. So this is why utility-side planning about generation resources, reducing emissions, would be very important for Bellingham, because we have abundant hydropower, wind, and solar here in Washington State. There's no reason why these bars for electricity should even really exist. They should go way down. And then the other legs of the stool is let's change natural gas combustion for heating water and homes and commercial buildings here and here to electricity. All right. So here are the global warming potentials. It's called global warming potentials because it's grams of CO2 equivalent. It's really just total greenhouse gas emissions in terms of grams CO2 equivalent of selected electricity sources. And so you can get this is a good snapshot if you're looking at the emissions per unit electrical energy generated. So this is grams per kilowatt hour. It's also kilograms per megawatt hour. It's just multiplying both denominator and numerator by 1,000. So coal is the worst. These are the median values here. So this is pulverized coal. It's a way to drive a steam plant. Gas combined cycle, recall from ENRG 380 or 101, it's taking a jet engine, a Brayton cycle, and then taking the exhaust from that and boiling water to drive a Rankine or steam cycle. So you get to use the heat energy from the gas twice in a way. So this is the most efficient technology. So it has median values of 490 grams per kilowatt hour. If we're talking about a single cycle natural gas combustion power plant or NGCT, natural gas combustion turbine, these are just the jet engines turned on their side. So-called peaker plants, they have emissions around 600 or so, and that's because they're not taking advantage of that waste heat to drive a Rankine turbine to make more electricity. Biomass is tricky to calculate. It has a huge range. It depends on how old the biomass is that you're burning, where it came from. It depends on if you're growing a fast-growing tree like a poplar or something and burning those, then it can have really low emissions because you just recently pulled that carbon out of the atmosphere and then you're releasing it, so it's closer to neutral. Whereas if you're burning older forests or other things, agricultural waste, then it can have higher emissions. It's tricky to calculate. What exactly are you saying you're emitting? Where did it come from? How recently did it leave the atmosphere before you put it back into the atmosphere? Solar PV, I've never seen this value, 180. That's insane. This is usually the value I see, around 45-ish. It's all associated with melting sand to make the silicon, right? That's thermally intensive, takes a lot of energy. If that energy comes from a carbon-intensive source, then the scope 3, the embodied carbon for PV is higher.
Do you have a guess as to where that 180 came from at all?
So my guess is that's a terrible plant installed poorly somewhere that doesn't get much sun. So the capacity factor, recall from 380 or 101, is how much electricity is generated by a plant over the course of a year divided by how much energy it could have produced nameplate if it was running full out all the time. And so even a perfect solar plant put on the moon or something, that wouldn't work because it doesn't rotate the same way. A perfect solar plant put on the Atacama Desert, where it's sunny all year, would best achieve 50% because it's going to be nighttime half the time. Realistically, probably like 35% because it's not high noon all the time. I guess if you had tracking, then you might get that closer to 50%. Capacity factors here in Bellingham for solar is about 16-17%, sometimes a little better. But the lion's share of solar thus far has been installed in, well, at least as of 5 years ago, it's probably China at this point. Yeah, it's definitely China at this point. But before, it was installed in Germany, and they had a capacity factor of like 11%. And so if you're saying how many grams of CO2 are produced per kilowatt hour generated, the per kilowatt hour is going to get smaller and smaller and smaller with lower capacity factors. So if you're installing solar in a crummy location and you did a bad job and you had a bad angle, then you're not going to produce that many kilowatt hours over the course of its life. And so then the grams of CO2 embodied in production of that solar power divided by an ever smaller denominator is going to make that number get bigger. So I wouldn't pay too much to that maximum for solar panel. It just means somebody did something stupid. Whereas this 910 for coal is pretty common. These older plants that have been going since the 70s are definitely up on this side of the spectrum. All right. Geothermal, similar to solar, it's all about the embodied carbon, the scope 3 emissions, maybe a few parasitic emissions from operating the plant itself. Wind is super low, and that's because it doesn't take nearly as much material as solar panels. You only need 3 sticks versus this whole square of material. And so the embodied carbon per unit energy generated from wind is really low. Hydropower can be exceptionally low. This all depends on how long the hydropower plant lasts. Long-lived hydropower plants, it continues to decrease because that denominator, the kilowatt hours generated, continues to increase. I forget where this horrible number is, this 2200. I'm guessing it's this, there's this hydropower plant in Brazil that was recently built like in the last decade or two. And they flooded this huge region of the Amazon, and it only has a head of like 10 meters because it's such a flat area. And so they went with huge volume of water going through very short head. And when you flood a big region like that, especially somewhere in the tropics like that, you create a lot of anaerobic decomposition. So all these plants that you've now flooded in the floodplain and permanently put underwater, they decompose without oxygen and make a ton of methane. There was a study out of UW, I think like 6 years or so, that showed hydropower done wrong can be the worst. And so that's probably where that value came from. But in general, something like Grand Coulee Dam here that's been around for 100 years, that's at 1. And it's still just generating gigawatts of power, every second. Yeah, here's nukes. It's pretty good. Wind onshore is great. This is my pick for low carbon energy is wind, and then solar second. My pick overall for renewables would be solar, just because you can put them anywhere. All right. So this table tells you where all these emissions come from for electricity. So if you look at a balancing authority like PSE, then you say, well, what are the resources? How much do those resources produce? And then you get some average balancing authority emissions, grams per kilowatt hour. A condensed list from the EPA, including global warming potential values for methane at 25, so like the AR4 values, not the AR5 values at 28. It just shows you how increasing the efficiencies, this is like kind of the dumbest step you can do to lower your emissions if your Puget Sound Energy is. Let's upgrade our natural gas turbines and our coal power plants. Let's clean them, make them more efficient. And so you can go from average coal of like 1 gram per kilowatt hour, or 1,000 grams per kilowatt hour, 1 kilogram, to efficient coal at, so you reduce your emissions by over 10%. Good. You're still like spewing out a tremendous amount of emissions. Average combined cycle gas turbine versus an efficient, newer combined cycle gas turbine. So that's kind of the first dumbest step you can do, is just make your fossil fuel generators more efficient. Here's some details from CO2 from electricity use. This, I think, is from lecture 2, but let's go over it again. This equation that we've seen over and over again, amount of CO2 you emit depends on how much fuel you consume and the carbon intensity of that fuel. And for electricity, we have to concern ourselves, particularly with fossil generation, and only with fossil generation really, is this heat rate. So how many gigajoules of chemical do you need to put in to get a megawatt hour of electricity out? How many gigajoules of coal? How many gigajoules of natural gas do you need to put in these generators to get a megawatt hour out? So it's the reciprocal of efficiency, right? It's pay over get instead of get over pay. You also have to take into account line losses. So when you deliver electricity, these electrons travel over power lines. There is some resistance to those wires. That resistance increases with distance, and it increases with temperature outside. And so those line losses are the delivered electricity that you actually receive, not the electricity that is generated, is 1 minus the percentage of loss multiplied by the generated electricity. Typically, they're assumed to be about 7% for America. So the total amount of fuel combusted that first part of that equation, fuel, depends on the heat rate, how much fuel you have to put in per megawatt hour, and then these line losses. So as line losses increases, this denominator becomes smaller and smaller than 1, lesser and lesser than 1, and so it grows the amount of fuel you need.
Is there a way to decrease the line losses, or like, is there any technology or people working on making the line losses less?
Yeah, totally. So transformers are a big issue. Those things, you can hear them groaning as it gets hotter and hotter outside. They start going like, so more efficient transformers, solid state rather than analog transformers. And then thicker wire has less resistance. It's more expensive though, right? Changing different wire materials. And then the big deal is when you're traveling long distances, is switch from AC to DC. But that's kind of a balancing act because that transition from AC to DC requires these things called thyristors that have their own losses involved. So high voltage DC transmission has the lowest losses. All right, good question. In terms of efficiency, if you're given the efficiency of a power plant rather than its heat rate, then you can figure out the efficiency from the heat rate or figure out the heat rate from the efficiency by looking at, the unit conversion from gigajoule to megawatt hour, and then you just invert it, right? So you get over pay, and then you have this little conversion, that there's 3.6 gigajoules per megawatt hour. And so the amount of CO2 emissions in terms of efficiency is the carbon intensity of your fuel multiplied by the amount of fuel you need. So that's the efficiency of your power plant, which is down here, 1 over the efficiency. So as the efficiency increases, the amount of fuel needed decreases. And then line losses are included here. And then this is just a conversion factor from gigajoules to megawatt hours. All right. This is all stuff I said, but I wrote it down too, apparently. Okay, yeah, so to go from heat rate to efficiency, you have this conversion factor, and then you have 1 over efficiency. So this is again an example from lecture 2, but we can compare coal to gas. I'm going to run through this a little more quickly. So this is gas-fired power plant. Heat rate of 7,700 BTUs per kilowatt hour. Again, you want the smaller the number is better for heat rate. It's how much fuel you put in to get a kilowatt hour out. So this is equivalent to 8.1 gigajoules per megawatt hour, going from BTUs and kilowatt hours to gigajoules and megawatt hours. And this is equivalent to being 44% efficient. Assuming 8% T&D losses, I don't know why it's 8%. I said 7% a slide ago, but we're going with 8% now. And so we have our heat rate multiplied by the carbon intensity of our fuel divided by 1 minus line losses. We convert from kilograms to metric tons. And we see with natural gas, we have 0.44 metric tons per megawatt hour. So this is a very nice combined cycle gas power plant. The average, again, was like 490 or 0.49. So this would be a very efficient gas-fired combined cycle. Comparing that to a coal-fired unit, higher heat rate, meaning that it's not as efficient. So if we go through this conversion again, we see it's 33% efficient, and this worse efficiency and much, much higher carbon intensity, because the ratio of carbon to hydrogen is much higher in coal, yields this 1.09 metric tons of CO2 per megawatt hour. So nearly over twice as bad as coal. And so that's why America was able to keep its emissions from electricity flat while its economy continued to grow. We were producing more electricity because we are phasing out coal and replacing it with natural gas. So we can basically have twice as much natural gas electricity per coal electricity and keep emissions flat. But this doesn't take into account methane leakage. And we'll talk about that in a sec. So, I don't know who, but somebody already asked a question about how do we reduce some of these reduction options. And again, let the math be your guide. Look at this equation. We can change the carbon intensity of the fuel, so switch from coal to gas, or better yet, switch to wind or solar. We can change the efficiency of our power plants, clean our power plants, use better things. Or we can reduce our line losses. And so this equation tells us something we can do on the supply side for all these things. Heat rate improvement, cogeneration, get more electricity out per unit fuel put in. Fuel switching, go from coal to biomass or natural gas. Yeah, you can take existing coal power plants and retrofit them to burn something else that's pulverized. Renewable generation. Yeah, so there's a plant in Sacramento that they switched from coal to burning almonds and pistachio shells and Christmas trees. Renewable generation is even better fuel switching. Nuclear generation is another fuel switching option. This is what France did. They have the lowest carbon intensity per GDP of any nation in the world. And that's because they have 71% of the electricity comes from nukes. But there's obviously other problems associated with it. France actually hasn't had a problem with it, though. England, America, and Russia, and Japan certainly have, though. You can capture the carbon on the back end. So that is something to do with changing the carbon intensity. It's kind of strange because it's still producing that carbon, but you don't let it go into the atmosphere. T&D losses, more efficient transformers, conductors, voltage support, power factor, and reactive power management. This I don't even know about. I'm not going to even pretend. But some weird like imaginary numbers happen with electricity. Any electrical engineers in the class, they can help me out. You get these things kind of out of phase, pushing back against the power and make it not as useful. That's about all I know. Also, a lot of this equipment, this power equipment, power grid equipment, requires, you don't want it to oxidize. So they displace the oxygen with a heavy gas, and the heavy gas they use is this sulfur hexafluoride, which we've talked about earlier. It's that stuff that you can breathe in and makes your voice really low because it's heavy, but it has an insane global warming potential. So 1 pound of sodium hexafluoride is greater in terms of global warming potential than 10 metric tons of carbon dioxide. And so if these breakers and transformers leak this sulfur hexafluoride, that's a huge global warming component. Okay, so that's under the hood how these emissions are calculated. What you'll probably use in your career, and certainly in this class, is these aggregated average emissions per balance authority or per power grid. And these can be found from the Environmental Protection Agency's eGrid. And it's a report that they generate about every 2 years, and it's always kind of 2 years delayed. So a report just came out in January. It was revised again in March, and it's eGrid 2020, but it's actually reporting 2018 data. And so we can have a quick look at that. So I linked to it on Canvas. Let me make sure I'm not lying. Yeah. So here's the eGrid 2016 data. So I made this before the March report came out. So that's why it's even older. So this is the 2018 report relying 2016 data. To get the current report, again, go to that link that I have listed here in the PowerPoint. Maybe I'll put a link in Canvas too. Or just Google EPA eGrid, or eGrid will work. And it takes you to this website. So here's eGrid 2018 released. Again, the real one came out just recently, March 9th, 2020. And so you can click this eGrid data file, Excel. There's also some good supporting documents to tell you what they're actually doing. These summary tables is just like the quick dirty look at it all. But yeah, you can look at maps to get if you're into GIS, you can get shape files and things like that for making maps of carbon emissions or whatever you're interested in. So if you look at a sub-region map, you can see Electric Reliability Council of Texas, ERCOT, And then see like we're part of the Northwest Power Pool. CAMEX is where CalISO operates. So yeah, you kind of see how things are laid out. So if we open up that big Excel file, which I've done here, let me zoom in on it a little bit for you guys. So it has this table of contents page, which is pretty handy. And so these are basically, it's like a zoom level. So sheet 1 is down to particular units. So, you know, Ecogen downtown may I forget how many they have. They may have like 4 units, 4 generators within that one power generator plant. And then zooming out, you can look at Ecogen itself, the generator, or these are units part of a generator, and then you can get all the way to the plant level, and then you can get to the state level, which I don't think is nearly as useful as this sheet number 5, balance authority, because this determines what your customer, if you're a consultant or even just a residential customer, this tells you what your client or your own emissions are per kilowatt hour. So if we click balance authority, you guys probably can't read that at all. Let's zoom in. So yeah, here's City of Tacoma right at the top. Alcoa, so is that the one nearby here? Or I know Alcoa has a few locations. Okay, so let's go down to PSE. Public. Puget Sound Energy. Okay, so that's where we purchase our electricity from. And then these columns have all sorts of things up here. And so we have how much fuel got put in these insane numbers. But let's get to the stuff we care about. So we have NOx emissions, sulfur dioxide, annual CO2 emissions, annual methane emissions. And it's an American unit, so we have tons, not tonnies. So these are 2,000 pounds. And then for the smaller, the GWP gases, it's in pounds. So you have to do a little conversion when you're doing this kind of analysis. But thankfully, they calculate the CO2 equivalent for us. And I read their recent release, and they were using Assessment Report 2, which was dumb, but now they're using Assessment Report 4, which is still pretty dumb, but it's not as dumb as using Assessment Report 2. So if you want to do the emissions really properly with Assessment Report 5, then you'd have to do this calculation yourself. But for the sake of, you know, your own personal emissions or working with a client, or certainly for the sake of this class, I'm totally cool with using Assessment Report for CO2 equivalents. And so this is how many total tons of CO2 are emitted in 2018. But better yet is the per megawatt hour. So if we keep scrolling over here, did I pass it? Yeah, column Y. Balance authority, CO2 equivalent total output emissions, pounds per megawatt hour. And PSE is at 569 pounds, so I don't know what that would be, like 250 or 260 or something. 280 kilograms of CO2 per megawatt hour equivalent. Okay, so that's how you can get the emission output for different places. Compare that to Seattle City Light, just down the I-5 corridor, and we went from 569 to 1.9. This is why Puget Sound Energy sucks. Look at that. There's no emissions. That's because it's all hydropower. Other nearby places, here's Chelan County, 0. Snohomish County down the road, 0. These are public utility districts that pride themselves on having 0 emissions. So all their new resources that they're purchasing is wind, solar, and a small scale run-of-the-river hydro. So yeah, it just sucks. I mean, it's amazing that these places are doing this, but we could do a lot better. Okay, we can look at other places that make us feel better. Ohio Valley Electric Corporation. Oof. So recall coal is 1,000 grams or 1 kilogram per megawatt hour. No, that's per kilowatt hour. It's 1 metric ton per megawatt hour, and there's 2.2 pounds per kilogram. So what are they burning in Ohio? Straight up coal, right? That's how they get that 2.2 value. And it's even more than 2.2 because we have some line losses. So yeah, there's some places where a Prius will most certainly be a Tesla Model S, but they're few and far between, thankfully. I don't know how this one's negative. I don't know what's going on there. I don't even know where that is. That's curious. I'm guessing either they're sequestering carbon or they have some sort of like offset going on, like planting trees.
There's
Cool.
another negative one.
Yeah, that's funny. They're both in the ENRG. Yeah, I don't know how that's happening. City of Homestead. Anyway, so yeah, you can go all the way to like a generator. So why is PSE bad? Well, they own this coal power plant called Coal Strip in Montana. That'll take forever to get to. What's the state code for Montana? MT?
Yep.
Okay. FL, Kansas, MA, ME, MN, MO, MT. Oh, it's a small state. Yeah, so yeah, here, Coal Strip. This is all Puget Sound Energy stuff. And it doesn't tell you the CO2 per megawatt hour, but it tells you how many megawatt hours are generated, and then it tells you that it's a steam plant, and it tells you what it's burning, sub-bituminous coal. So then you can figure out the carbon intensity by looking at the heat rate of sub-bituminous coal and the carbon intensity of sub-bituminous coal, and then you can calculate how many kilograms of coal you needed to make this many megawatt hours, and then you can figure out the carbon intensity. So it's an incredibly rich data set, lot to find in here, but for the sake of this class, you'll be using sheet number 5, I think, this balance authority, when you're working on your projects. You can look at the US average, and it is 952. You guys probably can't see that. It needs to zoom in. 952 pounds per megawatt hour, so 500 kilograms per megawatt hour. It's natural gas, and that makes sense because here in America we have some really good stuff like wind, solar, and hydro, some really bad stuff like coal, but mainly we have natural gas, and so it all averages out to about gas. So there's a lot of room for improvement on the supply side here to reduce our emissions. Okay. Better than eGrid, if you can find them, are internal reports. And so this is an internal report I obtained from Puget Sound Energy. I'm not sure if they wanted me to have it. They were telling me how many customers they have, but then I found this paragraph talking about their carbon emissions, their CO2 equivalent emissions. And so eGrid 2016 PSE has this 204 kilograms per megawatt hour. The PSE internal report reported 1042 pounds, which is equal to 472.6 kilograms per megawatt hour. So their internal report is nearly twice as bad, or over twice as bad as what eGrid states. I don't know what the discrepancy is there, but eGrid is calculated centrally, either in DC or Argonne National Lab in Chicago, and they're trying to collect data from all over the place, and so it's second-hand data, right? Whereas this internal report is first-hand data. They say their green power is 0.03 kilograms per megawatt hour. That's absolutely impossible. I don't know how that happens unless they have some offset. Like you shouldn't be able to achieve zero. I know like Chelan, I think. When I first moved here, I said Chelan, and people got really upset. Chelan County and Snohomish County have these really low numbers. I don't know how you get these this low unless you're like buying carbon offsets. I did a back of the envelope calculation. If Puget Sound Energy took coal strip and converted it to gas, their internal report should go from 472 to 300, so that'd be a big improvement. But they're still burning a lot of gas, whereas like Seattle City Light is using hydropower. Okay, and then here's wind, solar, and some other renewables, but I'll get into that in a second. So, idea one was efficiency, clean up your power plants. Idea number two for supply side is fuel switching. So, decommission your coal power plants at 1.09 metric tons of CO2 per megawatt hour and build natural gas power plants at 0.44 metric tons of CO2 per megawatt hour. Or better yet, build wind and solar. Gas is attractive because it's very dispatchable. What's that mean? It means that it's on demand. You can ramp up gas production or dial it back based on the demand of the power grid. Problem with natural gas is that it leaks methane, which is intense global warming greenhouse gas, right? So assessment report 5 says that it's over a 100-year time scale. It's 28 times more potent than CO2. And so if it leaks anywhere along the chain from the well, the production well, all the way to the point of combustion at the power plant or your home, then methane will be leaked directly into the atmosphere and have that big global warming potential. A paper came out a couple years back by Alvarez in Science, and they looked at, they tried to calculate the U.S. leakage rate, and they used a couple different approaches. What we really need is ubiquitous sensors to look for methane. But their estimate is 2.3% well to point of combustion, and they say that it's likely greater than this. And they said most of this leakage comes from just a few bad operations. So, you know, a cowboy frack pad somewhere in Colorado or Midlands, Texas, and it's just leaking like crazy and nobody's paying attention. But that being said, even though it's a few bad actors, apparently, the leakage rates on average are 2.3%. So for all the gas produced in America, 2.3% goes into the atmosphere. And clearly this is happening the world over, because you can look at this graph here that shows methane concentrations in the atmosphere increasing with time. So there you have it. What do I have here? Leaked equals rate times demand, 1 minus rate. Careful with the math. It isn't rate times demand. Okay, yeah, so I see people make this error all the time in industry. And they say, well, if the leakage rate is 2.3%, then we'll just multiply that 2.3% by how much gas I consumed. But it's not by how much gas you consumed, it's how much gas was produced. So, I mean, I don't know why I'm thinking in beer, but so say you order a pint of beer, if half of it got leaked along the way, it got spilled, and you still ended up with a pint of beer, that means a whole nother pint got spilled somewhere, right? So that leakage rate would be 50%. You end up with a pint, but that means over 2 pints were poured somewhere. It wouldn't be you ended up with a pint, and if the leakage rate was 50%, half a pint got leaked. So you have to be careful with that math. Maybe I should just do this math just to make it more clear. Okay, so we have a gas frac pad, we have some pipe, and then we have power plant, right? We have this leakage rate, and I guess it equals 2.3%. So that's just gas leaking off. Over here, this is our demand. How much gas we need to produce electricity. And back here we have our production. Okay, so let's think about this. The amount leaked, L, isn't 2.3% of demand, it's 2.3% of production. So the leakage equals rate times production. But all you really know is demand, right? Because you don't know how much was actually produced. You know how much you bought at the power plant. Your client knows how much they purchased. They know the gas they purchased. They don't know how much got leaked along the way. And so we can set up another equation so that we get a system of equations. That way we can figure it out. So let me think about this. Yeah, so we have, with these variables, we can also say that production equals demand plus whatever leaked along the way. That makes sense, right? Production equals, not rate, it equals leaked. Production equals leaked gas, that's up here, plus demand. And so now we can substitute this in for here. So production equals demand plus rate times production. We're trying to figure out how much got leaked, so we can rearrange some of this stuff. Am I doing this right? Yeah, so P minus RP equals demand P1 minus R, yeah, equals demand. So therefore P equals D over, sorry, doing math on the fly is always tricky. P equals demand over 1 minus R, so then the amount leaked, which equals RP, is going to be RD 1 minus R. So it's trickier. It's leak does not equal RD. It equals that. Make sense? All right. Is that what I put on the slide? Rate times demand over 1 minus rate. Cool. Yes, math works. This is the same as this. All right. And so what does this mean? This was, I think this was from Cascade. No, I mean, this was from BP, a BP report, and they're trying to show that carbon capture and sequestration can be a really good thing. And so they're saying that because of these methane leaks, average gas is actually, 25% worse than we think because of this leakage, and that if we have carbon capture and sequestration, then that leakage actually dominates here, and the leakage from coal is less. So then coal with carbon capture and sequestration is equivalent to natural gas with carbon capture and sequestration. It's still 4 times worse than solar, and 6 times worse, 7 times worse than wind. But it is an argument for carbon capture and sequestration, but man, that's expensive. Okay, so let's look at renewables. This is what we actually want to do. So these carbon life cycle assessment reports, they're all LCA reports for wind and solar, and they've been aggregated by Garvin Heath and a few others at National Renewable Laboratory. And they did this life cycle assessment harmonization studies where they took like 100 or so papers on solar and wind and tried to look at the scope and the boundaries of their LCA analysis, and harmonize them such that like they try to include the same things and remove the same things in that scope 3 emissions to try to find an average or a generalized carbon intensity for renewables. And so these are all scope 3, and that's why the carbon's all embodied in the upstream. These are LCA terms, sorry if you haven't taken the LCA class. So this means things that carbon was emitted when we extracted the materials to make a solar panel and when we processed those materials and produced the panel itself and installed them. There's a little bit of CO2 due to system maintenance and replacing things like inverters for solar panels. And then there may be some CO2 released when we decommission the solar panels at the end of life. But on average, it's 39 to 49 kilograms per megawatt hour or grams per kilowatt hour. So really low compared to coal and gas. Wind's even lower. Again, most of all the CO2 is concentrated in the upstream, embodied CO2 in building the thing. Comparing that to gas, we're at 420 to 670 kilograms per megawatt hour. There's still a lot of upstream emissions, right? This is a complicated machine that requires a lot of energy and CO2 to build. That being said, those upstream emissions are completely dominated by the fuel cycle because you're lighting carbon on fire and making CO2. And this is why renewables are so great, because they don't have operational CO2 emissions, really. Problem with renewables is they are not flexible, and so we need power grid flexibility to put them on the power grid. So this chart shows solar insolation, wind generation, and power demand down in Portland on a particularly nasty April back in 2010. And so you can see that power supply does not correlate with demand at all over the course of those 30 days that all these curves are superimposed on each other. So how do we get grid flexibility? We could have things like smart grid, smart controls. We could have things like energy storage, deferrable loads. So don't run water heaters at certain times of the day. Don't charge electric vehicles at certain times of the day. Or another option is we can just really overbuild wind and solar and curtail it when we don't need it. So, but if we build storage, that's going to add a few more carbon emissions. So if we, let's not look at this quite yet. Let's look at the math of that. Can I get a new page? So frustrating with these zoom controls at the top, always in my way. Okay, so if you think about, again, kind of production and demand, the production now going into a battery came from the power grid. And then it goes into a battery. And out of the battery is the actual demand from the consumer. And so how much comes out depends on the efficiency of that battery. And so the actual production is going to be P over the efficiency. And so the carbon intensity of that production, of that electricity, it's going to have some metric tons per megawatt hour, but now we have to multiply that by 1 over the efficiency. So this is the actual greenhouse gas intensity of that electricity. It's the carbon intensity of whatever your source energy is, and then that grows by 1 over the efficiency. And so if it's perfectly efficient, 100%, then it's just going to be the carbon intensity of that electricity. But if it's only 90% efficient, like a lithium-ion battery, which is the most efficient battery, then now for every, so if we power that with coal at like 1 metric ton per megawatt hour, multiplied by that 1 over 0.9, our carbon intensity is now something like 1.1 metric tons per megawatt hour. So carbon intensity of electricity grows with inefficient storage. What's that mean? Don't put garbage into batteries. Be careful with how you charge your battery. So something like time of day carbon emission, real-time carbon emissions would be incredibly useful. And that's something I've been trying to work with PSC on creating. Okay, so this is an analysis I did for Shell Oil Company. We were looking at a hydro battery they want to build on the side of the Columbia River over in eastern Washington. And so this analysis looks at the embodied emissions associated with building storage plus those emissions that are grown due to the inefficiency of those batteries. And so the overall emissions, the carbon intensity, kilograms per megawatt hour, depends on what kind of battery you're using. And so that's what all these different letters mean. PHS stands for pumped hydro storage. Lithium ion is obviously lithium ion. VRB is like vanadium redox. CAES is compressed air energy storage. So these are just different flavors of storage. And then these colors represent different generation sources. So where does that electricity come from? Wind and PV are the least carbon intensive, wind being the least, PV being the second. And then I have a few different power grids that I got from that eGrid data set. So we have the Pacific Northwest grid average, Colorado Rockies grid, US grid average, and then just a pure natural gas grid as comparison. And so you can see what really matters, more so than even the storage itself, is what you're charging the storage with. So putting clean energy into the storage is really important. There's a few exceptions, right? Lead acid batteries, they're the cheapest, but they're the dumbest, right? They only last like 500 charge-discharge cycles, and so you have to keep on building the battery over and over and over again. They're made out of lead, so they're super heavy, and so they're very carbon intensive. But in general, charging reasonable batteries with low carbon electricity is the best option to go with. And this still, even, battery plus renewables is still way better than natural gas, and that's the point I was also trying to make here with this chart. That people say, well, we can't do renewables because they're unreliable, and then you have to build storage, and that's going to increase the carbon intensity. Yeah, you're right, but it's still way lower than gas. Michael Moore.
Charlie? Yeah. Where did you get this?
This chart?
Yeah.
Oh, I made it. Do you want it?
Yes, please.
Yeah, so this is, I got the carbon intensity from NREL for renewables and for various power grids from the eGrid data set. And then I got the embodied carbon for batteries from a handful of papers that have been written over the last couple decades. I harmonized those results in a paper I wrote back in 2013. So then I took those values from that paper I wrote, and then I got the efficiency values recently and kind of fed that all together. And so the total carbon emissions. How did I just get a new page? So frustrating. Just press enter a bunch, I guess. Total carbon emissions from storage would be something like this. GHG storage equals GHG embodied, and this would be per megawatt hour capacity, and then plus carbon intensity of source. So this would be kilograms per megawatt hour. I guess this would be kilograms. And then, I don't know what my pen's doing, sorry. It'd be 1 over the efficiency of that battery. And that's a plus sign there. So you're adding the scope 3, the LCA embodied carbon, to the operational carbon. So it's kind of similar to like our money calculations, right? This would be like CapEx and OpEx. All right. Project Drawdown did a nice consolidation of supply side emissions and how much could be reduced. So if we switch from the US grid average to wind turbines or solar farms or geothermal, we could avoid this many gigatons of emissions, I think by 2050, I think what their target was. So this graph isn't directly useful because it has a lot of mathematics contained within it, and these time horizons like 2050, but it's a nice qualitative picture of what we should be doing on the supply side. I think the last slide is this. So I focused entirely on supply side. For your projects, for Bellingham, Washington State, etc., or you're even just a household, you could think about producing a marginal abatement cost for different demand side options. And so you can make your house more efficient, swap out your light bulbs, insulate your house. Deferrable load is an interesting thing. So I'm sure you're all familiar with the duck curve in California. The CO2 intensity of California's grid is really low at high noon because so much solar is online. So the carbon dioxide emitted per unit of electricity is really low at noon, but that's not really when people are using electricity. And so if we had something like a smart water heater that decided to, so you take a morning shower, right? And the water heater is like, oh, I have cold water in my tank, I better heat it up right away. But nobody's using that shower right away. And so it could wait till noon and then charge the water heater, and then maybe somebody to take an evening shower, and the water heater will still be plenty hot for that shower. So don't charge it right away in the morning, right after someone takes a shower. Wait till the carbon intensity gets really low. And then smart devices like Nest thermostats. These are all ways of reducing the electricity emissions from carbon emissions from electricity on the demand side rather than the supply side. So these are just some ideas you can have for your projects. Something I'm interested in is how can we use energy storage to avoid high carbon electricity, like things like Tesla Powerwalls or even electric cars or water heaters. Just charge them when the carbon's really low. Here's some mathematics on how do you calculate the total energy efficiency might be available. It's kind of the similar calculations we were doing with the light bulbs way back, like what's the population, what's the activity, and so similar for light bulbs is like how many square footage of lighting do you need. So we've seen all this before. I just wanted to include this on this lecture slide. And then to calculate the cost of saved energy. Again, it's you're calculating how much energy you avoided, but how much did it cost to avoid that energy. So recall for like lighting is something like 2 cents per kilowatt hour, and that's cheaper. That cost to save that energy to buy those lights was cheaper than the cost of the electricity on the power grid. So it makes sense to do those kinds of improvements from a financial perspective. And so to calculate that, you take your capital costs, you analyze them with the cost recovery factor, and then you add the operating costs, and then you divide that by how much energy you save by making that efficiency upgrade. And that gives you this cost of saved energy, which is a useful tool. All right, that's it for today. Thursday, we're going to go over the homework like we usually do. I think it's fun and it's good. And this homework is looking at, we're going back to Pebble Beach. Instead of swapping out all the lighting, we're now thinking about getting rid of some of the natural gas combustion on site and trying to purchase electricity from a cleaner region. And then, yeah, deciding about when to charge golf carts and things like that. And then the second half, we look at how wearing better clothes can have a negative MAC by reducing air conditioning needs. So the assignment looks long, but it's actually certainly easier than the last one. So have a look at it, and then we'll do it together Thursday.
Brilliant.
Any questions? Looking at the chat. Any concerns, comments, advice? Pleas of desperation. I know I haven't been grading the homework. I'll get on that this week so you can see how you're doing, but you should all be doing pretty well if you attend or view the study sessions on YouTube. All right, have a great day. Be well. See ya.
Thank you, Charlie. Bye.
My pleasure. Bye.